Hello and welcome. In this section, we will learn about moments and center of mass and see how we can use integrals to calculate the center of mass of a two-dimensional object. First of all, let's talk about the concept of the center of mass. The center of mass of an object is the point about which the object balances. This can also be thought of as the average location of the object's mass. So if we were to take an object and if we were to balance it above its center of mass, it would perfectly balance about that point. We're going to think about finding the center of mass for several different systems. First of all, we're going to think of a one-dimensional system, just with several points distributed along the x-axis. Then we'll think of a discrete two-dimensional system, where we have points in the two-dimensional plane. And finally, we will consider a two-dimensional continuous system, which is called a lamina. So let's start by thinking of a one-dimensional system. And to set this up, let's look at something called the law of the lever. Here we have two masses that are both placed on a beam of negligible mass, and we have a fulcrum here, which is the point at which these objects are balancing. So we're imagining that the objects are perfectly balanced around this point. It turns out that if we multiply the mass of one object times the distance from the balancing point, that's perfectly equal to the mass of the second object times the distance that it is from the balancing point. So we have this relationship here. As long as these objects are balanced, mass times the distance for each one is equal. These expressions are called moments. We can think of a moment as describing the tendency of the object to turn about the fulcrum point. Now let's talk about how we can use this equation to find the center of mass for two objects along the x-axis. So we'll draw on the x-axis here. It doesn't really matter where the origin is, but we have one object that's at an x value of x1, and then another object at an x value of x2. And this first one has some mass m1, and the second object has a mass of m2. Now, if we imagine the x-axis being a beam that is holding these two masses, there is some point in the middle about which the beam is perfectly balanced. That is the center of mass, and we denote that using x bar. So let's imagine that it's maybe right here. This is the center of mass. We'll call it x bar. So at this point, if we were to place a fulcrum, these objects would be perfectly balanced on this point. Now let's express this formula from the law of the lever to find out what the value is for x bar. The distance from the first mass to x bar is right here, and that distance is x bar minus x1. So we can think of that as the distance d1. The distance from the second mass to the center of mass is x2 minus x bar. This is the value of d2, that second distance. Now that we have these expressions, we can put them into this equation and solve for x bar. So we have m1 times d1, which is x bar minus x1. That must equal m2 times d2, which is x2 minus x bar. We want to solve for x bar to get an expression for the center of mass in terms of these different values. So let's distribute. m1 times x bar minus m1 times x1 equals m2 times x2 minus m2 times x bar. We want to solve for x bar, so we'll isolate x bar on one side. m1 x bar, we'll add m2 x bar to both sides. So we add m2 x bar, and then we want to add m times x1 to both sides. This should be an m1 x1. So we have m1 x1 plus m2 x2. Now on the left, we have a factor of x bar everywhere. We can factor that out. So we have x bar times m1 plus m2. This equals m1 x1 plus m2 x2. We can solve now for x bar by dividing both sides by this expression here. So we have x bar equals m1 x1 plus m2 x2 divided by m1 plus m2. We now have a formula for finding the center of mass if we have two different masses, as long as we know what the x values of those masses are. We can generalize this. Let's suppose that we have several objects. Let's suppose that we have n objects, and their masses are given here, m1 through mn, and they are at points x1 through xn along the x-axis. The total mass of this system is just the sum of all the individual masses. So the total mass we'll call small m. It is m1 plus m2, etc., etc. And the moment of the system about the origin is the sum of all the individual moments. We call this capital M, and this is the sum of the individual moments. Then the center of mass is given by this equation here. And notice that this is just an analogy for the 2-point case. If we have n points, we just generalize the formula that we just found for 2 points, and we can find the center of mass if we have n points. So this expression will give us the center of mass for points distributed along the x-axis. Let's take a look at an example of this. Take a look at example 1. Here we have 5 objects distributed along the x-axis, and we have the different x values of the coordinates here and the corresponding masses of the objects. Ultimately, we want to figure out what is the center of mass. But first, let's think about the total mass, and then we'll find the moment m of the system about the origin. So the total mass is just the sum of all these individual masses here. So the total mass, small m, is 7 plus 2 plus 3 plus 1 plus 5. These numbers add up to 18. Now let's think about the moment of the system about the origin. And as we do that, let's go ahead and plot what this would look like. So we have just the x-axis here. Here's the origin. And we have objects at -6, at -1. We have an object at 0. We have an object at +2. And we have a mass at 3. And I'm going to go ahead and draw in little circles to represent these masses, and I'll try to draw them according to scale. So at 2, we have a mass of just 1. That's pretty small. At 3, we have a rather large mass of 5. At 0, we have a mid-sized mass of 3, something like that. At -1, the mass is 2. And then at -6, we have the largest mass of all. We have a mass of 7. And we want to figure out what is the center of mass for this system. So let's write in our different values for the masses. This is 7, this is 2, this mass is 3, this mass is 1, and this last one is 5. Now notice here that we have a mass of 2 at -1, and we have a mass of 1 at +2. These are actually going to cancel each other out around the origin. If we think of the law of the lever, -1 times 2 and 2 times 1, those distances are the same from 0, so these 2 points individually by themselves would just balance around the origin. But we have all these other masses here, so we need to find the moment of the entire system to find the center of mass. So the moment, capital M, is 7 times -6, plus 2 times -1, plus 3 times 0, plus 1 times 2, plus 3 times 5. We have the masses times the x values. And if we simplify this, we get -27. Now the center of mass is the moment divided by the sum of the masses. So this is capital M divided by small m. Capital M is -27 divided by small m, which is 18, and this simplifies to -1.5. That means that the center of mass of this system is right about here at -1.5. If we were to add a fulcrum there, the objects would perfectly balance about this point. Let's now consider the two-dimensional case. If we have a two-dimensional discrete system, that means we have a bunch of different points, and instead of just thinking of points distributed along the x-axis, now these points are allowed to be anywhere in the plane. So the two-dimensional discrete system will look something like this. We have the two-dimensional coordinate axes, and we have a bunch of different points here. We'll try to draw different sizes to represent different masses. And the center of mass will be the location in 2 dimensions about which all these points would balance. So maybe it would be something along, maybe right about here for this picture. Now it turns out that to find the center of mass, we can think independently of the x values and then think independently of the y values. And we use the same exact formula that we used in the one-dimensional case to handle just the x direction and then just the y direction. So if we look at the formula here, focus on the formula for x bar, the x coordinate of the center of mass. We have this m sub y, and m sub y, this is not a typo, this should be a y. It is the moment about the y-axis, the tendency to tilt or to rotate about the y-axis. M sub y is the sum of all the moments, m1 times x1, that's the numerator here, and if we look at this x component for the center of mass, that's exactly the same as what we had for the one-dimensional case. The y component for the center of mass, that is the y analogy, just using the y values from these points. So for a two-dimensional discrete system, we just apply the one-dimensional formula twice for the two separate components. M sub y is called the moment of the system about the y-axis. That's again measuring the tendency for the system to rotate about the y-axis or to tilt about the y-axis. M sub x is called the moment about the x-axis. That is measuring the tendency of the system to rotate or tilt about the x-axis. Let's use these formulas to work through example 2. So for example 2, we have a bunch of two-dimensional points, and at each of these points we have a mass given in the table below. Let's go ahead and draw a picture for this and then answer the parts of this question. So we have a mass at -4, -2, which is right here. We have one at -1, +3. We have one at 1, -3. And we have a mass at 3, -1. The mass at -4, -2 has a value of 2. The mass at -1, +3 has a value of 3. And the mass at 1, -3, that's right here, this has a value of 5. And the mass at 3, -1 has a value of 2. We want to know what is the center of mass for this system. And we could maybe guesstimate what this would be. The largest mass is right here. We've got another one here. I would guess maybe somewhere around in here would be the center of mass for this system. So to find the total mass, we just add up 2 plus 3 plus 5 plus 2. 2 plus 3 is 5 plus 5, 10 plus 2. That is 12. That's the total mass of the system. To find the moment about the y-axis, we take the mass values and multiply by the x coordinates. So we will take 2 times -4, 3 times -1, 5 times 1, 2 times 3. We're using the x coordinates to find the moment about the y-axis. This is not a typo. So the moment about the y-axis is 2 times -4 plus 3 times -1 plus 5 times +1 plus 2 times +3. 2 times -4, -8, minus 3, -11 plus 5 is a -6, plus +6, this value is actually 0. That is the moment about the y-axis. This tells us that the system is perfectly balanced across the y-axis. Now, what is the moment across the x-axis? Well, we take the y values, multiply them by the masses, and add the result together. So this is going to be m sub x, 2 times -2, plus 3 times 3, plus 5 times -3, plus 2 times -1. 2 times -2 is -4, plus 9 is +5, minus 15 will be -10, minus another 2 would be -12. So this is -12. Now the center of mass is x bar, y bar. X bar is the moment about the y-axis divided by the total mass. Y bar is the moment about the x-axis divided by the total mass. So we take the moment about the x-axis, about the y-axis rather, that's 0, divided by 12, that gives us the x component. So we have 0. The moment about the x-axis is -12. We divide -12 by 12, and we have -1. So the center of mass for this system lies at 0, -1, which is right here. That is the location about which all of these points will balance.